Thanks for showing up today, Jeff. It's good to see you in person.
Great to see you, Kwabena.
Thanks for inviting me out to your offices.
My pleasure.
Yeah, so today I'm meeting with Jeff, and I want to talk to him about our new cameras. We have two new systems coming out, and it's called the OpenMV AE3 and the OpenMV N6, which are based on the Aleph Ensemble microcontroller and ST's new STM32N6 microcontroller. And so I'm just sitting down to have a good conversation with Jeff about, what's happening in the embedded AI world, how can microcontrollers play a part, and just in general, what people are thinking about these days.
Yeah, really looking forward to talking with you.
Yeah, thank you. So Jeff, tell me about the Edge AI Vision Alliance. What's going on with your companies, the organization? How are things? What's been happening?
Sure. Well, I started running an engineering consulting firm over 30 years ago, working on embedded algorithmic applications like digital signal processing, where there was a lot of need for figuring out ways to run things very, very efficiently on low-cost, low-power hardware.
Mm-hmm.
And then around 2010, my colleagues and I realized that we were getting close to the point where it would soon be possible to deploy computer vision very widely. At that
Mm-hmm.
point, computer vision was a known thing, but it was for NASA and DARPA, not for, Whirlpool and iRobot.
Yeah.
But we could see what the trajectory was. We could see that, okay, in the next few years, it's going to become possible to put computer vision into just about anything. And that's going to be huge because computer vision can add so much amazing capability, make things easier to use, more autonomous, safer,
Mm-hmm.
bring them valuable new capabilities, etc. So we got very excited about that. We decided, okay, we're going to shift the focus of our engineering consulting business to embedded computer vision. We did that, but then we realized, there's no ecosystem in the industry for people who want to build products or want to enable people to build products with embedded computer vision. And that's going to slow things down. There's no place for people to go to learn from a practical point of view. How does this stuff work? What are the trade-offs? What are the pitfalls? What are the techniques that really work in the real world? So we decided to create this alliance, the Edge AI and Vision Alliance,
Mm-hmm.
really to do two things mainly. First, to raise awareness and provide practical know-how. So people building all kinds of everyday electronic systems would realize that, hey, maybe I can actually put computer vision in this thing and learn how to do so. And then secondly, to help foster connections in the ecosystem so that, for example, somebody building a kitchen appliance that wants to put computer vision into it would know, well, who are the suppliers that can provide me with, let's just say, smart camera modules or
And
software development tools.
how to make it even happen, right?
Exactly. So that's what the Alliance is about. On the one hand, helping raise awareness and provide practical know-how for product developers so they can figure out where it's appropriate to use computer vision and related forms of Edge AI to make better products and help them get connected to the technology suppliers and other resources that they need so they can be successful. So that's kind of how we got started almost 15 years ago.
I actually want to drill in that point because I feel like there's some interesting history back there. So when you first started and before 2010s, what were you guys doing with these embedded systems? Tell me about some of the projects you guys were working on.
You mean before we started working on computer vision?
Well, just before 2010, as you said, that inflection point.
Yeah, well, we were working on things like digital video, digital television, right? Things that were
TiVo?
Things like that, yeah. Things that where people were really pushing the envelope in terms of doing a lot of very intensive digital processing of real-world signals, in this case, video and audio, but in an environment where they were very cost-constrained,
Mm-hmm.
maybe also power-constrained. So you had to be really thoughtful about, if you just kind of did the straightforward thing and took the textbook algorithms and implemented them in the standard way, then the set-top box is, $1,000 and burns 200 watts and it's completely uneconomical. So how are you going to get that to be a $200, 20-watt set-top box? Well, you're going to be clever about using specialized processors and optimizing the algorithms and the software at many, many different levels of abstraction so that you can actually get these things to run efficiently in real time.
Mm-hmm.
So we were doing that in other domains, and then we saw And it became possible to do that largely because of improvements in the processors, right? Things like digital signal processors or even CPUs, first desktop and then embedded CPUs that added things like single instruction, multiple data
SIMD
instructions so that they could do these kinds of algorithms more efficiently. And then we saw, oh, you know what? The same thing that just happened here in like digital audio, digital video is about to happen in computer vision.
Yeah.
The chips are becoming more and more capable, more and more efficient, and pretty soon we're going to be able to put computer vision in just about everything. The closest analogy I can come up with is when I was in grad school, late 1980s, studying digital wireless communication. Digital wireless communication was pretty much fully understood. The only problem was it was prohibitively expensive for 99.99% of the potential applications where it would be useful.
Is that like SDR, talking about software defined, or
not limited to software defined, but just you think about you're probably not old enough, but if you could remember back to 1990 and think about, well, where would you find digital wireless communication? The answer was, well, government agencies and big corporations and data centers, not consumers, not everyday people, not small businesses. Now it's so ubiquitous we don't even think about it. Our wristwatches have computer vision. Have digital wireless communication.
Yeah, Bluetooth. Yeah.
Our thermostats have digital wireless. Everything has digital wireless communication because it makes everything better, and it's become cost effective to put it everywhere. What we saw is, we're right approaching the beginning of the same thing happening with computer vision. It's so useful. I would argue actually way more useful than digital wireless communication. It's so useful. It will go everywhere once we make it economical to go everywhere.
It's funny you say this because I can see digital wireless communication or just wireless stuff everywhere nowadays, but computer vision is still on your phone or in some kind of box that is locked and plugged into the wall. And it isn't really like everywhere mobile yet, per se.
It's starting to be.
Yeah.
You got to look for it, but it's out there. It's certainly on the phone for sure.
But it's only inexpensive items.
That's changing, though. Think about best counterexample I can come up with. Well, I'll give you two great counterexamples. First one, doorbell cameras. I was visiting a few months ago a neighborhood where the whole neighborhood was just built a couple of years ago. So it's like all brand new houses. And walking down the street, what I noticed was literally every single house had a doorbell camera or some kind of, maybe not doorbell, but home smart camera. And they were all different brands. So it wasn't like the builder installed them in the houses. Clearly, there were aftermarket things homeowners had bought and added to their houses. And every single house had one. And as you know, these are like, I have in my house the Wise cam. It's $35. This is a very capable smart camera that's $35. So there are some counterexamples. Another great one is if you like coffee, the Keurig coffee brewers, you put the pod in and close the lid.
Yeah.
They have multiple models now of the Keurig coffee maker that use computer vision. The way it works is you lift the lid, you put the pod in. As you start to lower the lid, if you look closely, you'll see a flash because it's taking a picture of the pod so it can tell which of the, I think there are about 5,000 varieties of pods, which of the 5,000 variety of pods you're using today.
Yeah. And
it can track your consumption. So they can tell you, hey, Kwabena, you're about to run out of your favorite coffee. Would you like to reorder? But also they adjust the brewing parameters, the water temperature and flow rate and so on, based on what you're making. So let's say if it's hot cocoa, they figure, well, probably making that for a kid, so we'll lower the temperature so the kid doesn't burn their mouth. So that's a sub $200
But I would say,
consumer
though,
product.
The Keurig one, though, is a better example than the WiseEye because it's actually doing computer vision, per se. It's running algorithms on those images. I think there's a difference between it just captures video.
The WiseCam, believe it or not, is doing real-time computer vision.
Okay.
Yeah, it's quite astounding what they're able to do in a $35 camera.
Okay, so they're actually identifying objects and tracking people and such?
Yeah.
Okay.
It's very impressive. So I agree, not quite ubiquitous yet, but starting to become so. And the place where it's kind of quietly become ubiquitous and you don't notice it unless you look for it is cars. I defy you to go buy a new car or just look at one in a showroom that doesn't have at least 6 cameras, right? And growing, right? Cameras in the side view mirrors, rear-mounted camera, forward-mounted camera, in cabin camera for driver monitoring and occupancy monitoring. 5, 6, 8, going to 12 cameras per car. And like automakers, that's a brutally competitive business. They're not adding cameras for fun or for the novelty of it or just say they have 12 cameras. They're adding, each of these cameras is like they did the math down to the penny and decided, you know what, that's
Valuable.
a good investment to add that extra whatever it is in the bill of materials, because that's giving us some essential functionality that the consumer is going to pay for, or increasingly regulators require, like in the case of automated emergency braking.
Well, backup cameras also are now standard, right?
Yeah, but not just backup cameras, smart backup cameras that, so if you're not looking, it's looking, and it's going to apply the brakes.
Yeah.
If you're about to run into someone or something. So it's interesting because we're not really aware of it until something happens. Like I was driving a car I hadn't driven before, maybe a year or so ago, an entry-level Toyota Corolla, and driving on a freeway in the mountains, and suddenly it started doing lane keeping assist. It started steering itself to stay in the lane. And it kind of freaked me out because I wasn't expecting it. I'd never driven a car that had that before. So then I realized, oh, okay, I know what's going on here, right? Those cameras in the side mirrors are watching the lane markings. It would have been nice to know ahead of time that it was coming. But anyway, my point is, we don't notice there are all these cameras mounted in and around the car, but we when we need them, right, for automated emergency braking, for lane keeping, for whatever, then we're appreciative that the functionality is there.
Yeah, but I think there's a common thread being all throughout this, which if we go back to the time you were working on optimizing algorithms, for set-top boxes and things back in the day, for every single one of these applications, you'd have to care about how much the compute cost, how much power it draws. You have to actually have really well-crafted code also that works on these. You can't just throw something over the fence that has not been optimized and expect to actually ship a product in volume. Would you say that's about right or so?
Yeah, that's been kind of our focus in the work that my colleagues and I have been doing for 30 plus years. And it's very much still the case in the realm of embedded computer vision and related types of applications that efficiency is absolutely critical. One of the things that our industry association, the Edge AI and Vision Alliance, does is we conduct an annual survey of commercial system-level product developers who are incorporating computer vision or similar technologies into products, or who want to but aren't, and understanding their technology choices and their pain points. And to me, one of the most interesting questions on the survey is, we say to people, well, if there's a place where you're not using computer vision in your product, where you want to be, why aren't you? What is preventing you? By far, the two most commonly stated answers why I'm not using computer vision in places when I want to are the hardware cost and the development cost. Okay, so what does that tell us? Well, hardware cost tells us, well, we need to find more efficient ways, right? We need more efficient processors, more efficient algorithms, compilers, et cetera, so we can get these algorithms running in real time on hardware that's inexpensive enough that it can go into, well, whatever it is we're building. Maybe it's a $150 coffee maker, whatever it is. And the second part tells us, well, we need to make it easier. And these things are usually opposed, right? If we need super efficient software, usually it's not easy to develop. Usually that's when we're writing assembly code, right? We're working at very low levels of abstraction. It requires a lot of detailed knowledge. It's very error prone. It just takes an incredible amount of time. So we need to find ways to get the efficiency, but also improve the ease of development so that the hardware is affordable, the bill of materials cost is affordable for whatever the target application is, but also the development cost is affordable. Back Mobileye doing automotive safety computer, they were incredible pioneer in this space, perhaps the first company to really develop mature, sophisticated driver safety systems using computer vision. At one point, they had like 1,000 engineers working on algorithms.
Wow.
Okay, good for them.
I feel like that's like the size of, I remember reading a book about Intel building the Pentium processor, and they had teams that large.
Right. So amazing. Glad they could do that and basically like trailblaze this whole field. But how many companies can do that? Like can allocate 1,000 engineers to a project? Almost none. Right. So we've got to find ways to both get the efficiency and bring the hardware costs down, but also just make it a lot easier so that your typical product development team can can implement these capabilities in their product.
Yeah, no, and I think this is a good point for me to introduce my company, OpenMV. The way I got involved with the Embedded Vision Alliance is I've known Jeff for quite a couple of years now, actually. Not part of the alliance officially, but just as someone I'd bump into at random conferences. So about the OpenMV Cam, basically OpenMV was a hobby project that me and my co-founder Ibrahim we got started doing back in 2015, actually, 2010s. And what Ibrahim noticed, actually 2013, is that these microcontrollers were getting fast. The STM32F4 came out, and it had a DMCI bus, I think, or DCMI, one of the two. It had this parallel interface bus that could attach a camera to it, and you could stream camera into its RAM. And that took care of the image capture problem, which was hard to deal with because cameras have a very bursty way they transmit data. It's kind of like all the bytes come back to back nonstop. If you can't handle them, you just drop the image. And so it was one of the first MCUs that had this feature built on board. It had nothing else, though. You can just capture an image, and then there was no processing logic or anything else there. But we were able to write some basic algorithms, and we got stuff like color tracking. And actually, Ibrahim made a port of the Vialo-Jones HAR Cascade face detector to the OpenMV Cam, and it could actually run a HAR cascade and track someone's face. And that was running on a STM32F4. Fast forward, ST came out then with the F7, and I actually managed to put the April tags algorithm and run that on board. This usually took like I think this algorithm normally would have like 10, 20 megabytes of RAM necessary to do anything, and I managed to fit it in 512 kilobytes, going back to like optimizing code. But when we were able to pull that off and we got QR code detection working on board and barcode detection also working, we started to get some juice behind this idea that microcontrollers actually were capable enough to run computer vision algorithms. Back at this time, if you Googled computer vision on a microcontroller, the only thing that came up was a Stack Overflow thread about people saying, no, absolutely not. OpenCV will never run on microcontrollers. And that was the wisdom of the day. And so in the last 10 years, things have changed greatly. We're actually seeing now, like ST came out of the H7 after the F7, and that was the first microcontroller where the performance of the system really got to a point where you stopped running into like crazy bandwidth limit issues. You also had a JPEG compressor in hardware, which allowed you to start producing high quality images for viewing, getting them off chip. And you really started to see the promise of this. Like, okay, it's not able to push everything in every direction all at the same time, but we're starting to see the performance, we're starting to see the ability. And a new shift is happening that is going to change things dramatically. This year, with the new STM32 N6, we now have microcontrollers that have like almost a teraflop of compute on board. This is a huge gain. So the previous systems maxed out at about 1 gigaop or so. 1 or 2, that's about all you had. And so over here, with the OpenMV Cam AE3, this features ARM's new Ethos U55 processor. And this guy has 204 gigaops. So it's 200 times faster than the previous generation systems for ML, meaning that all of a sudden you're not stuck with just doing color tracking, which was our bread and butter application.
Yep.
That hobbyists love that, but industrial folks not so much, because you can only do so much of color tracking. All of a sudden, we're able to take an AI algorithm that used to run, let's say YOLO, that would run at 0.3 frames a second on the STM32H7. So 0.3 frames a second. So you get 1 frame every 3 seconds. Mm-hmm. Sometimes worse. If you run a larger model, it's 0.06 seconds per frame. Mm-hmm. So it's not in real time at all. Anyway, with these new systems now, thanks to all that extra horsepower, all of a sudden this means you're going to be able to run a model now at 25 to 30 frames a second on board this little guy right here, and then 60 FPS plus on the STM32 N6. And this is that exponential curve that I think you were watching from the sidelines, where you're starting to see the promise of these microcontrollers. They're starting to get faster. And then all of a sudden, you were dropping now 100x, 200x speedups. And the implications there are going to be big. Like, how do you think this is going to affect the industry?
Yeah, it's super exciting. And one of the people I most admire is Dean Kamen, who is best known as the inventor of the Segway scooter, but in fact, his main focus is inventing medical devices. And also, he started the amazing FIRST Robotics program, which uses those April tags that you mentioned. And early in the life of our conference, we run an annual conference in May called the Embedded Vision Summit, which is designed for people who want to incorporate these kind of capabilities into systems and want to learn what's the current kind of practical state of the technology and what works and what are the trade-offs and so on. Well, I noticed that some engineers from Dean's company were showing up at our conference. I thought, that's strange, because I wouldn't have expected Dean's company, DECA Research, which does a lot of medical devices and things like that, to be interested in computer vision. But I got in touch with Dean, and I said, I noticed this, and I'm really curious, and would you come and speak at our conference? And we were very fortunate that he agreed to come speak at our conference. And if you know about Dean Kamen's work, you know that feedback control is kind of the essence of his inventions, right? That Segway scooter is entirely enabled by feedback control, and many of the medical devices,
right? Yeah,
because of feedback control, exactly. The feedback control. And Dean had a very interesting take on this, which I think your products start to really bring into reality. He said, my vision is that computer vision, a smart camera module, is eventually going to become kind of the moral equivalent of what a limit switch is today. Like limit switches, if you're designing electromechanical stuff, you throw them in everywhere. They're cheap, they just work, and they're kind of a basic part of the design engineer's repertoire. Or maybe if you think about more in the processing realm, microcontrollers are like that, like something like a Raspberry Pi or an Arduino. Everybody coming out of school, in some kind of embedded EE, mechatronics, robotics, they all know how to do things with Arduinos and Raspberry Pis, to the point where if you ask a current engineering graduate, oh, hey, I want you to flash some lights, they'd probably use something like an Arduino to do it versus you and I might do a 555 timer circuit with some capacitors and some resistors, but they're just going to program an MCU because that's their kind of language. They know how to do things. Well, Dean's message was, my vision is these embedded computer vision enabled camera modules are going to become that ubiquitous. We're going to use them everywhere because a smart camera module is essentially a software defined sensor. What do you want to sense? Well, let's just take one use case. Let's take a camera looking at your face, Kwabena. Well, what might I want to know? Well, I might want to know who you are, right? Face recognition. I might want to know, are you present? Face detection. Maybe I want to know what your mood is. Are you actually enjoying this conversation?
I am.
Different muscles get used if you're faking a smile versus if it's a genuine smile. What's your mood? Are you intoxicated? Because if I can see your eyes, right, I can. What's your heart rate? What's your blood pressure? Are you sleepy? Are you, falling asleep? All these things, right? I can sense with a camera.
So much information.
The right algorithms, right? Just about anything you'd want to sense, you can sense. It sounds like a crazy idea that camera modules become like limit switches, because camera modules have been freaking expensive and complicated, right? But you guys at OpenMV, I think, are doing great work, trailblazing, making them much less expensive and also much easier to use, so people can start thinking about putting them everywhere and making all kinds of systems and devices more capable, smarter, safer, easier to use, because they have this increased awareness about what's going on around them. So this is where I think Dean, when he first said this, camera modules are going to become like limit switches, it sounded just insane. But the more I've thought about it, and as I've seen how the technology has progressed over the last few years, so now it's not much bigger than a limit switch.
No,
right?
When I think about that, we look at the OpenMV AE3. If we see this little guy here, it's the size of 1 inch by 1 inch. And we crammed on there a global shutter camera that can run at hundreds of frames a second, a time-of-flight sensor, a microphone, and an accelerometer gyroscope. So 5 sensors at once with a 200 gigaopt processor and Wi-Fi Bluetooth. So if you think about that, that thing you can put in a light switch. It can now turn on the lights if you're walking by. It can be used as the face detection sensor to, again, turn on all kinds of applications. I can't list them off in my head right now without some particular customers I'm thinking about. But it's like, we're getting there. We're getting to that point. And I think that was one of my original ideas when I saw this project. Ibrahim conceived of the OpenMV Cam, and so it was his idea coming from this. And we actually wanted to build this thing called the OpenMV Cam Micro a long time ago that actually went up in flames. And so we're happy to have finally able to actually generate this, the idea of being able to make a small camera module. To talk about that, we made something similar to this same size, 1 inch by 1 inch, a while back, but we didn't have good electrical engineering support at that time. I didn't know what I was doing. It was more of a hobby project. And let's see, we ran the processor at 3.3 volts, and it had an internal regulator on it. And so the heat injection of just it down regulating the voltage to power itself. If you think about it, like injecting 0.1 watts of power into a PCB board doesn't sound like a lot, but if you integrate that over time, your board actually becomes burning hot. Mm-hmm. Anyway, so for this one though, we don't have that problem. We've actually managed to create a product that kind of goes towards that need of being a camera that can be used as a limit switch, as you say.
Yeah, it's fantastic, and I really am very impressed with the work that you guys have done. For a very small team, you've really achieved an incredible amount, and these latest modules are super impressive. One question I'm sure is on many people's minds is, well, how much are they going to cost?
How much are they going to cost? Okay, so we're going to be unlocking and releasing the OpenMV Cam AE3 for $80. That's the goal. Kind of aggressive pricing, honestly. Doesn't leave a lot of margin for us, but we really want it to be popular, so we're trying to put that at a price where everyone can buy it. With the inflation and tariffs happening at the same time, it makes my life a lot harder, but we'll try to be around that price as much as possible. And then for the full system over here, this is the OpenMV Cam N6 of a FLIR boson. Don't ask what the FLIR boson cost. You can go Google that and be horrified. It's a really awesome camera. That's for the industrial customers, but the baseboard, which is the OpenMV Cam N6, we're aiming at about 120 or so.
And that'll presumably work with other less expensive camera modules as well, yeah?
Yep. So we have a few different types, actually. We're going to have, we have our bread and butter older cameras like the OV5640. Not necessarily going to manufacture that anymore, but it'll still support it. We actually have a company called Prophecy that we're working with, who is an event camera. So this is exciting. We have this in stock now in our store. And so with the event camera, you're going to be able to sense motion and detect things. It has a nice feature in that it's HDR. So it works indoors, outdoors, with huge dynamic ranges. But then it doesn't really need lighting because it only sees single pixel changes. So it can work in dark environments and bright environments. But best of all, it has no frame rate. You can set the frame rate to be whatever you'd like. And this allows them to do real fun stuff for VR applications, like track LEDs very, very fast. Mm. You also have a global shutter, the same as on the OpenMV Cam AE3. A FLIR Lepton, which is a much more affordable thermal camera than the FLIR boson. And then finally, we're going to be offering a new HDR camera from PixArt Imaging. That'll give you 5 megapixels of resolution. Very
cool. And I think you guys have a Kickstarter coming up?
Yeah, we do. Not coming up, it's running right now. So if you've enjoyed this conversation and like to get on board and check out these new systems, please back the Kickstarter.
And tell us a little bit more about the Kickstarter.
Yeah, so we've launched these new products and we're raising money to put them on sale and such. And, given that you have to go out and do any kind of advertising and marketing anyway to get the word out, we thought it's best that we launch a Kickstarter, see what things people like, get people involved, and go out there and spread the word.
Excellent. And I think you guys are also going to be present at the Embedded Vision Summit in May and giving a talk on related to these products. Is that right?
Yeah, I will be. We have some cool ideas that we're going to be discussing. So one thing that we do at OpenMV is we work on MicroPython. It runs on top of C, so C is in the backend. So every algorithm actually is written in C, but we use MicroPython to compose the operations. This allows the programmer to focus on kind of the high level and not focusing on loops and such. Imagine if you wanted to blur an image, like the median filter, for example, or the mean filter. We'll have a one-line function call that does that, and then in the back end, there might be SIMD code going on to do all that work. Lots of crazy loops, maybe like quad loop, 4 deep nested loops doing all kinds of stuff. Because you have the kernel being slid around an image, so really it's 4 loops, just in general. You don't really want to be writing that all the time and maintaining that, and so we take care of that effort, and then you're able to program in program in Python. But the reason I mentioned that is we're going to be talking about some cool novel ideas using TensorFlow and NumPy at the same time running on board the system, and we're going to be showing off a new way of programming where we're leveraging higher level thought processes and putting those on a microcontroller, getting you closer to a desktop level experience, but on an embedded system.
I think that's so important, given what I mentioned earlier about the development costs being one of the 2 top obstacles that people cite when we survey actual product developers. Hey, what's preventing you from incorporating computer vision into your product? So raising the level of abstraction. So yeah, I'm not having to write that 4-level nested loop and oops, I had an off by 1 error on my indexing or whatever.
Then you corrupted your RAM.
Yeah, just call the library function from a high level.
I'll tell you a side note. So we were working super hard for CES to get these things ready to go on sale. We wanted the demo for CES well. And we had one of those, what the most fun bug is? It's when you corrupt memory and then you find about it later. So hard to figure out what's wrong because you don't know where the corruption happened.
Right.
And that's what programming in C gets you exposed to.
Sure.
So one of the superpowers of being able to program in Python is once you have a Python library that is decently well debugged, and the library calls themselves could corrupt memory for sure, that's a problem. But assuming that the library has actually been well, written and it doesn't have any crazy problems like that anymore, you never get exposed to those kinds of issues.
Now you mentioned TensorFlow. What is kind of the recommended path for me getting my deep neural network onto the OpenMV cam?
Yeah, so there's really only one play in town right now for microcontrollers, and I kind of hope it stays that way a little bit. I mean, there's definitely companies who are doing their own custom software stacks that work their own custom way that you can have models running on board. ST has a tool chain for that, which will allow you to get models on the N6. There's another way of going right now, which is Google did a lot of work with something called the TensorFlow Lite for Microcontrollers library. And so this is an open source project they've been building up. I guess Google owns it, but also the code is pretty much Apache licensed, I think, and it's just available online for anyone to download, no restrictions. And so with that library, that's how you get models running on board the OpenMV AE3 with the Aleph Ensemble processor on board and with the ARM Ethos U55. And so one of the benefits of the library that TensorFlow Lite for microcontrollers is that it runs on all microcontrollers. So this allows us to abstract the hardware, and it means that if you have a TensorFlow Lite model, I can have this running on an NXP processor, I can have it running on an ST processor, I can have it running on the Aleph processor. It doesn't really matter, Renaissance, whatever you name it, it can run on board these CPUs. And then if they have an accelerator like an Ethos U55, that then plugs into the TensorFlow Lite for micro library and then accelerates the operations it can. And so this allows you then to move to a realm where you're not having to think about custom tools for a particular microcontroller. You can focus on just, let me tune this model. I can get the desktop performance good enough, working the way I want. And then when I deploy it on the system, it's going to run the same way.
So if I have some new deep neural network topology that I'm using and I get it to run using TensorFlow Lite for microcontrollers, and then I come to your booth at the Embedded Vision Summit in Santa Clara in May and say, hey, Kwabena, here's my model file. Are you just going to be able to get that to run on the OpenMV cam?
More or less. We support hundreds, I think like 100 plus operations from TensorFlow. I will say you need to stay in 8-bit integer quantized realm. So just like I think people were finding out about LLMs and the need to quantize the weights so you can make them run on less GPUs. It's the same for all of these embedded systems. They all run on quantized weights. So typically, the particular quantization you want to use is int8, so 8-bit integers. Not uint8, int8. I'm actually not quite sure why they picked one or the other, but I think it has to do with the scaling and offset, and just int8 was the one. Some accelerators have support for int16, but generally that's rare. So the mainline support is all 8-bit integer quantization.
Got it. So generally the development flow would be, I develop my model in whatever TensorFlow or whatever desktop environment I want. I quantize it. I port it to TensorFlow Lite from microcontrollers. And assuming I've quantized it to int8 and I've got it running in TensorFlow Lite for microcontrollers, I should then be able to get it to run on the OpenMV cam. And for my pre and post processing operations before and after my model, I'm going to use MicroPython and call your library functions for things like scaling and so on. Yeah?
Yeah. No, we have support for that. And for these new processors, actually, they have GPUs on board, which is really cool. And so we previously wrote a software GPU, actually, that did bicubic, bilinear, and nearest neighbor scaling in software. Very proud that we got that to work. First implementation, I think, that actually was high performance for microcontrollers to do that. But for bilinear scaling now, you don't even need to leverage that code. We actually offload that on board the GPUs on board these things.
Interesting. So there's GPU compute on a microcontroller.
Yeah, it's crazy. Now, now, let me be clear. These GPUs, they don't handle vector operations or anything like that. They're just meant for like doing basic drawing, like take an image, blend it onto a target place. But they have the basic feature of they can take an image and then they can scale it for you and blend it onto a target buffer. And so for all your neural network operations, you always need to crop and then scale to feed it into the network activation window. And so being able to offload that in hardware is a huge help because the amount of time it takes to do that can actually be longer than it takes the MPU nowadays to actually execute the network.
Very cool. Well, I got to say, Kwabena, I'm so impressed with what you guys have accomplished in the last year, and I think you're moving the industry forward on a couple of the, as the developer survey data tells us, a couple of the really important pain points: the cost of hardware and the cost of development. So really happy that OpenMV has joined the Edge AI and Vision Alliance as a member company, and really looking forward to seeing your demos and your presentation at the Embedded Vision Summit in May.
Yeah, thank you. All right, Jeff. Thanks for the great conversation.
Thank you. Good
I appreciate it.